Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
But next, we're very pleased to welcome Percy Liang to come and give a talk on the elusiveness of a specification of artificial intelligence. Percy is a professor of computer science at Stanford, I'm sure familiar to many of you as a core part of the machine learning community, and we're very excited to hear what he has to say. Thank you.
Is this your laptop? Hold on. Okay. Gotcha. All right. All right. Thanks everyone for coming, and thanks to the organizers for having me. So Nick talked a lot about used words like AI takeoff, superintelligence, sentience, and these things. And I guess the question for me, and maybe the researchers in this community, is what should we as researchers be doing about this? So a lot of people I actually talk to kind of say, well, that's that kind of interesting, but that's so distant. We barely have things working, and so, well, I'm not going to think about it. And you kind of saw a little bit of that sentiment in the last panel. So there's kind of this chasm here. And the goal of this talk is to try to bridge this a little bit. And so what I want to argue is that there are actually concrete underlying principles that we as researchers at a technical level can actually try to do, which maybe don't necessarily mention the word superintelligence, but nonetheless point in the right direction. Okay, so as we know, AI has been quite influential, and in the future, it's going to be even more. So I don't need to say much more about this. But I do want to reflect a little bit on what are we trying to do. So I think a lot of people are trying to maximize accuracy, right? But what should we be doing? Well, in some sense, we should be maximizing long-term societal benefit, let's say. But then the question is, I've written this nice equation, what is this function? So this is what I mean by a specification. What are we trying to actually accomplish? So here's the outline of the talk. It's centered around specification. I'm going to start at kind of a low level and trying to broaden into something that, and maybe get more speculative as we go. Okay. So the idea of a specification is really powerful, and it underlies a lot of kind of how you build modular and scalable software systems, right? So if you have the specification that sorts, you understand what it does, and then people can work on implementing it. So division of labor. And it's not just for kind of the systems, it's also for humans. It helps you scale up because it gives you modularity and scalability of thought, which is actually in some sense even more important. So what does this look like for machine learning? So today we've seen a lot of deep learning take off, for example, and I think a lot of that has to do with having these interfaces. You can write down a model, and you can have automatic gradient checking and automatic things happening, and this wouldn't be possible if you didn't have a specification of what you're trying to do. This is actually kind of important at the code level because once you try to get more performance out of your optimizer, so you have a computational graph and you want to actually optimize it, then you might risk the possibility of computing the wrong answer. So verification is actually kind of important. So I'll just highlight one thing that I've been involved in is this idea of formally verifying and constructing algorithms kind of in a joint way using basically tools from theorem proving. And there's a number of challenges there, which I don't want to really go into, but I just want to highlight this work. Like, how do you represent the specification in the first place, and how do you search this space efficiently? We have some preliminary thoughts you can ask me later. Okay, so moving on, computing gradients and making sure that you're optimizing a function correctly is all nice and well. But for example, this is a pretty well-defined specification. But what do we actually want? So the specification for machine learning is already a little bit more elusive, right? You get some training data, and you want to output a predictor that does well at test time. So in some sense, this is not really a specification because it's in the absence of any assumptions, it's impossible to verify. And so you need some assumptions. The classic thing that has driven basically all of machine learning is, whether you look at the theory or not, this is kind of what's going on. You get some training set, is basically your test set, or not your test set, but the distribution of examples is roughly the same, and that is what allows you to generalize. Okay? And you can, be a little bit more clever and say, well, it doesn't have to be exactly the same distribution, and we can still generalize a bit more. But this doesn't, I would say that the present theory doesn't really address these very large changes, like disasters and adversaries. So there's some work on adversarial perturbations of your input. But I would say those are kind of like you take your input and you tickle a little bit, right? It's not that your entire input just kind of goes, it gets completely disrupted. And so here's a picture that kind of, there's changes and there's changes, right? So a lot of, statistical work currently focuses on, kind of small changes between train and test distribution. But when you're thinking about, the long-term risk of AI, you need to think about possibility of something dramatic changing at test time. And you need to kind of have systems that can react to this. And so, of course, if your train and test distribution are completely different, well, what can you do? In some sense, you can't guarantee good accuracy. But I want to say that's OK. And I think it requires changing the specification. So instead of saying we want predictors that do well at test time, we want to say we want to predict something and give an estimated accuracy of how well we do. So the model here is know what you don't know. Some people say be aware of the unknown unknowns. And I think this is kind of a very important point. You can't win in the original game of just predicting accuracy if you want to be robust. You have to actually say if I get some arbitrary input that I don't know what to do with, I should punt on it. Okay, so and this is kind of a challenge because at test time, you don't have labels by definition of test time. So, silent failures are possible. Maybe the user changed his mind and wanted to do something completely different. And these are the worst because they're silent failures. So one thing that we've been looking at with Jacob, one of my students, is we don't want to assume that the train test distribution are the same. What we're instead going to assume is that there's some structural assumption about training and testing being similar. For example, you have the same setup of sensors, but some of them could be getting different readings. Maybe you have some conditional independence there. And then the goal is to, given a trained model, can you estimate the labeled accuracy on unlabeled examples? So, and this is still work in progress. We're still kind of working out the details. But you can think about this as an unsupervised learning version of model evaluation. Okay, so I think things like this is, I'm just giving you one example of something that I think is really relevant to the long-term risk of AI because we're dealing with these unknown unknowns. Okay, finally, I want to talk about, go back to where these specifications come from, right? So in our head, we have all these nice things that we want our AI systems to be able to do. But let's be honest, specifications are always going to be incomplete. Even in traditional software, you just can't write down everything that you want, right? So this is kind of should set off some alarm bells. You don't want to just go ahead and pretend nothing is happening because, for example, let's say you maximize classifier accuracy, right? Then you might end up discriminating against protected groups, especially if you use a discriminant classifier. If you say don't harm humans, maybe you end up locking them in a room. This example is from Nick. If you maximize paperclips, you could end up destroying the world or something. But so there's different levels of unintended consequences that you can imagine. And and these look very different, but the underlying principle is the same. The underlying principle is you have a large space of actions. Your specification is partial, so you just can't pinpoint down the behavior. It's a really simple idea, and if we're building more capable AIs, the action space grows, and maybe we want to be over here, but we could be over here. So there's a lot of unpredictability here, just due to the nature of the game that we're playing. Okay, so as an ML person, I would say, let's just learn the specification from data. Why are we hard coding in the first place? And data being humans here. Okay, so there's been, Nick mentioned inverse reinforcement learning. There's been a lot of work kind of coming from robotics, but also in other areas. And the question is, what would humans do? And so you get some human action sequences, and you want to infer the reward function or the values or the specification. But this also requires some delicacy here. First, you need to generalize in the right way from this data. And by the way, who are these humans anyway? Why should we be trusting them? Okay, so the point one, another way to say it is, in terms of like the statistical language, identifiability. So most of machine learning, not all, but most of it focuses on prediction. So we're basically saying, I want accuracy. I want a classifier that does well on input-output pairs on my distribution. But I want to argue that if we want to do inverse reinforcement learning, we want to be answering the why question, right? We want to actually identify the predictor or the value function or whatever. And here's a kind of an example diagram that explains why this is so important, right? The key is that the AI is going to actually operate in a different distribution than humans. So this connects with a previous statement I made about how it's so important to be robust to wildly shifting shifts in distribution. So if you train a classifier over here, you might just fit a linear function or something, right? So you have no idea what's going on over here. So you should either say I don't know, or or have a model that can actually identify the right function. It's not sufficient just to predict on the distribution that you're training on. Okay, so the second point is, who are these humans? Well, let's ask the question, who's in control? So there's a lot of talk about the control problem. And so here's what's going on. So we have the behavior of the system, and it's a combination of two things. The things that the system designer wrote down, let's call that the model, and then there's data, if we're going to be in this learning game, which I argue we kind of have to be. So behavior is a large number of bits. Model is a small number of bits by definition. You can't just write down everything. And data is also necessarily has to be a large number of bits. So necessarily the system behavior is dominated by the data. Okay? But so wait, where did this data come from? Well, it came from humans. So wait, what determines human behavior? Well, it's actually the system. Because in the modern world, actually, human behavior is actually driven a lot by systems. So you have this feedback loop, and I would say that even today, the majority of behavior defined this way, the majority of behavior of AI even today is not explicitly controlled by the designer. Maybe I shouldn't have said that, because now tomorrow in the news it'll be say researcher says AI is on the loose or something like that. But okay, and there's some attention to this already. So Leon Batua at Facebook, I guess this work was also done at Microsoft, is studying kind of ML in the wild, where you have users and you have advertisers and trying to get a hold of these feedback loops, which I think are really important to understand if we want to say anything about how AIs are performing in the world. And there's this other paper which appeared at NIPS this year out of Google, also addressing similar issues about feedback loops and other software engineering issues. Okay, so one point I want to make is that personally, I don't actually find the AI agents view very useful, because I think it's too much anthropomorphization, right? Instead, I think about in reality, I mean, AI already today is intertwined with humans. And I think in order to understand what's going on, we can't really just treat the AI system as a black box, study what it's doing. You have to think about the whole ecosystem. Okay, so just to conclude, a lot of people focus on accuracy, but accuracy is not the only game in town. So 3 things to keep in mind, I think, as takeaways for things to, I think, really make technical progress on, which I think will be for the better in the long term. Know what you don't know. You want to build systems which back off gracefully, not silently fail or crash catastrophically. I mentioned this idea of identification as opposed to prediction. And I want to emphasize this because so much of our community kind of focuses on prediction, is that if you want to extrapolate just focusing on prediction isn't really enough because you can't just look at your training examples and smooth a little bit. You have to actually think about the structural properties of your function. And then finally, if you want to actually study the system, I think in some sense the data is a place to look because I think that's where the most number of bits is actually comes from in terms of deciding on system behavior. So those are the three things I want to focus, and I just want to thank Jacob, who I have a number of conversations with, and the Future of Life for supporting this. So thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.